Say when.
That should be it now.
Well, good evening, ladies and gentlemen, and welcome to this meeting of Astronomy Ireland for November, a special month because it's Science Week all this week. And we're delighted to have this evening as our main speaker, Dr. Ian Sanders, again to tell us all about meteorites. You might have just seen his video on TV about a recent, interesting, perhaps potential fall. That's on our YouTube channel. Go and have a look at that if you want to see that. Tonight, though, I'm just going to briefly explain to you what's happening with our meetings, as ever. And then we'll have our main speaker who'll talk about it just under an hour, take questions at the end. So keep your questions until the very end, and we'll take them then. I'm David Moore, founder and editor of our magazine, Astronomy Ireland magazine. There's no glare on that, you can see it. A lot of you already get it, tells you what to see in the sky every month, and reports on what everybody in the country is seeing, as well as all the international discoveries every month. If you're a member, please get other people to join the society. We're always looking for beginners. If you're not a member, we set up Astronomy Ireland for you. Watching a lecture like this, you're overqualified. So our format of the evening will be just tell you a bit about what's been happening since our last monthly lecture, then our main speaker, and then some events that are coming up, especially for Science Week. There's going to be classes, talks in Tralee, Mayo, around the country, and a Saturn watch as well. So there's lots to stay on board for after the talk. It'll only take a couple of minutes. We'll also tell you what to see in the sky. There's a lot coming up as well. Most of it's in the magazine, but we'll briefly tell you about the highlights, things you can see with the naked eye that are really spectacular. So what's been happening since our last lecture? In fact, our last lecture was our October lecture, which was about robots in space, given by Dr. Elizabeth Pearson, who has written a book on the subject, Robots in Space. And those robots are not so much the ones that look like humans and move around, going beep, beep, beep. They are the robot spacecraft we have trundling around Mars at the moment and out in space doing lots of other really interesting things. If you missed that, you can get a copy of it on our website. Go to the lecture DVDs and you can order it there if you missed it. You can either have the online link or the actual physical DVD. These lectures are held every month. They go back decades. The society is over 30 years old now, and it's the world's most popular astronomy society. So do join. We're very much aimed at beginners and very family friendly as well. As always, we've been very busy in the media. It was Space Week back in October, Science Week here in November. We held a Saturn watch. The International Space Station was flying over morning skies, but the good news is it's coming to evening skies in a few days' time. But we also had a fantastic display of the aurora. Not last weekend. There was supposed to be one, but it didn't materialize. But the previous weekend, there was a fantastic aurora, widely seen from the south coast up to the north coast. And if you're interested in seeing the northern lights, well, go to our social media. You'll see the links to Facebook, Twitter, Instagram on astronomy.ie. And sign up for those. The aurora alert sent out each afternoon before sunset, telling you if there is one expected or not. And as well as that, we'll also predict when to see the International Space Station, but also if there's going to be any interesting space chases, new craft coming and going to the space station as well. And it's by far the brightest thing in the sky when it flies over. So well worth getting the kids out to watch. The other big event, of course, that we had last month was the eclipse of the moon. Now, some people thought the weather was bad, because we always tell you about the weather forecast. Ignore it. Do what I did. Stand outside in the rain. And eventually the clouds will break. They did. I got some incredible views, maybe only for a few seconds over the hour and a half, but also got some great photographs that you'll see in the next issue of the magazine. And other people either had better weather than me or were standing out in the rain as well. And they saw it too. So there's going to be a bumper issue of Irish eclipse photos from October the 28th in the next magazine. And if you miss it because you don't get the magazine, sign up for the magazine because there's another eclipse of the moon coming next September. And there's going to be an eclipse of the sun in April. And we always have a full guide and tips for each of those every month. So we've been keeping very busy as ever over the last month. We'll be very busy this week with Science Week. And I'll tell you about our Christmas lecture, The Science of Santa Claus, after our main speaker. And that does bring us nicely along to Dr. Ian Sanders, who's one of Ireland's foremost professional scientist in the field of meteorites, but he's also highly regarded worldwide. He got his education in Cambridge, and he's been working in Trinity College for more years than I care to remember. He's now officially a retired professor there in the geology department, but specializing in meteorites in particular. You may have remember, if you're old enough, back in 1999, there was a meteorite fall on Ireland, the last recorded one, November the 28th, I think it was. You may hear I've got a bit of a cold, and curious enough, I had a bit of a cold that night as well. I was in bed when the phone started hopping with people who'd seen this explosion. Eventually, a guilty-looking rock was found on a road in between. We predicted Carlow and Kildare, and bits of it were tested by Ian and other science as well, and shown to be an actual meteorite. So, with those credentials, we can think of nobody better tell us during Science Week of everything you need to know about meteorites. So, thank you very much, Ian, for giving the talk, and over to you.
Thank you very much, David. It's a pleasure to join you tonight and having a chance to share with you the things that I enjoy, meteorites in particular. So before I switch over to my slides, I would like to show you some specimens. I hope you can see this. It's a piece of iron, a little sawn slab of iron metal. And this is a piece of an iron meteorite. But not all meteorites are made of iron. In fact, only a few are. And similarly, this next piece, it's a piece of the rock called basalt. And some meteorites are made of this rock, an igneous rock, like comes out of volcanoes. And thirdly, meteorites are made of this stony material. In fact, most of them are made of this stony material. And if you can see, I'm not sure if it's catching the light, there are little shiny flecks of metal in this rocky material. Now, as well as these three which make up most, there are some meteorites, rather rare ones. This isn't a meteorite, this is a piece of earth rock, and it's made of a green mineral called olivine. And a few meteorites are rather like this, and I'll come to them during the talk. Here's a very obscure kind of meteorite. It's shiny metal, as you can see, but it's got big chunks of olivine embedded in it, just a small piece there. Okay, so with that, I will share my screen and start the talk proper. I can see it here. Yeah. And go to this slide and go to full screen. Hopefully, is that all working? Okay.
Yep, that's working fine, Ian.
Very good. Okay, so meteorite matters, a prelude to the planets, and we'll be learning as much about space and the planets as we will about the meteorites that we're going to see. So I'm going to start off by not talking about meteorites, but talking about space, because I'm just always amazed at just how big it is. And here is an image of a small body out there beyond the orbit of Neptune called Arrokoth. It's about 35 kilometers long, and it's a binary, two icy bodies joined together. And this was photographed in January 2019 by the New Horizons mission. And to get there, the spacecraft headed off, I think it was in 2006, and it went out past Jupiter, Saturn, Neptune, and little Pluto. Anyway, it got there. It's so far away that it takes 6 hours for the radio signals to be transmitted from the Earth to the spacecraft. And if you think that's a long way, 6 hours out to the kind of fringes of our solar system, it's 4.2 years for light to reach us from the nearest star, Proxima Centauri. And that's one of about 100,000 million stars here in our own Milky Way galaxy. Okay, so let's have a look at our galaxy. Well, it's best to see it flat on because it's like a huge fried egg. And to do that, we need to have another galaxy that's a bit like ours. And here's one that was recently photographed by Hubble. It's 150 million light years away. It's NGC 976 is its number. And there it is, most of the stars in a big cluster in the middle, like the yolk of an egg, and then spiraled arms around it. And if this were our own Milky Way galaxy, from one edge to the other, the diameter is about 100, got my numbers right now, 100,000 years for light to travel, 50,000 from the center to the edge. And our star, the sun, is about 2/3 of the way out from the middle. So that's 30,000 years for light to travel from the center of the galaxy to us. So if we're looking at the center of a galaxy through a telescope, we're looking at the center of the galaxy as it was before the Ice Age. So big is our galaxy. Well, ours is only one galaxy of 100,000 million galaxies. And to see those galaxies, the Hubble Space Telescope was pointed at right angles to the fried egg, looking through between the stars to find a chink where you can see through, because there's so many of our own stars, they get in the way. But when it looked, it was like holding a grain of sand at arm's length, that kind of cross-section of area. And what it saw was this, the famous Hubble Deep Field. It's nearly 30 years old now, this, but all those, apart from one or two nearby stars, all of those are galaxies, 100,000 million galaxies in the universe. And they are so far away that some of them, the light's been traveling for several thousand million years, going back to 12,000 or more billion, 12,000 million years ago. And in fact, looking back, one goes as far back, one can only go as far back as the Big Bang, which is about 13.8 billion years. So there's another image of deep space taken by the upgrade of Hubble, the James Webb Space Telescope. Okay, so that's a lot of stars in the universe. 100,000 million multiplied by 100,000 million. That's a 10 with 22 noughts as a rough estimate, anyway, of stars. Now, here's something that you're probably surprised to know. Here's a piece of coal, a small piece of coal on the weighing scales, and it weighs 12 grams. And 12 grams of carbon contains Avogadro's number of carbon atoms. That's 6 by 10 to the 23. So this small piece of coal contains about 60 times more atoms of carbon than there are stars in all the galaxies in the universe. There we are. There's pause for thought. Anyway, let's leave space and get to meteorites. And when meteorites arrive, they do so in a spectacular fashion because they're traveling through space at speeds typically of about 20 kilometers a second. That would take about 10 seconds to get from Dublin to Galway. They're going so fast that when they hit the atmosphere, they're very abruptly slowed down, and the friction causes the outside to get extremely hot and glow and melt and burn away until the incoming meteorite is slowed right down, and then it goes out, the fireball goes out, and it just drops to the surface. It's a heavy stone. And when such stones are picked up, here's one, a freshly found meteorite. You can see the surface is broken away a bit. You can see stony material inside, and on the outside it's glassy, black glass, which is the frozen remnants of that melting zone on the outside as it's coming through. Meteorites land literally anywhere. This, you would say, poor young lady had her car damaged by one. Michelle Schmidt, I believe her name is. And you think, poor soul. Anyway, her car became an item, and I think she sold it for more than enough to pay for the rest of her college education. So not always bad. occasionally, very large meteorites come in and they don't slow down. And when they hit the ground, they explode. And then you get a huge explosion, which creates a crater. And one of the best known craters is one, Meteor Crater in Arizona. Okay. Well, for all that meteorites land, very few of them are seen before they're found. Many more meteorites are just found lying on the ground, and they're found, many of them in hot deserts. This is the Nullarbor Desert in Australia, but more are found in the Sahara Desert, just lying on the ground. And they're also, here's an example. This is found in Namibia. It's a huge chunk of iron. It weighs 60 tons. It's the biggest meteorite that exists. This is a photograph taken in 1920. This huge iron meteorite. Okay, and as well as in deserts, many meteorites, more than in deserts, in fact, are recovered from Antarctica, from blue ice fields. In these blue ice areas, the ice is rising because the moving ice comes against a rock barrier below that makes it move upwards, and the wind blowing over the surface evaporates the ice, and all the meteorites embedded in the ice end up coming to the surface. So there's some numbers. The total number of meteorites that have been found lying on the surface or on ice is more than 65,000 different meteorites. The total number of meteorites seen to fall is only about 1,200. Okay, so where do they come from? Well, one way of finding that out, and it's being done more and more now, is to photograph them as they come in with a video. And this one was taken some years ago now, 4 images a second, and it was taken from 2 places at once. So it's possible to work out the trajectory of this incoming meteorite. And this has been done for many meteorites now. And this is back some years ago when 5 different meteorites had been tracked, and they have orbits that are highly elliptical, going around the sun, but way out, not as far as Jupiter, but through the asteroid belt here. These little dots are the asteroid belt. And we believe from this that meteorites are pieces that come to us from the asteroid belt. So why don't they just carry on going in nice regular orbits, circular orbits around the sun? Well, something called resonance happens. Now, this diagram, all those dots are separate asteroids, and left to right is the position, closer to the sun on the left, more out towards Jupiter on the right, and going up the diagram is the inclination of the orbit. And there's a gap here. No asteroids in this zone here, labeled 3 to 1. Now, what that means is that 3 to 1 is 3 laps of the sun by the asteroid coincides exactly with 1 lap of the sun by Jupiter. And when that happens time and again, every 3 laps, there's Jupiter in exactly the same place. That causes the whole thing to become unstable, and quite suddenly the asteroid goes flying off in a new direction and goes into an elliptical orbit and brings it close to Earth. So let's take a look at some asteroids. The biggest one is Ceres. It's about 1,000 kilometers across. It's really a dwarf planet. This was photographed by the Dawn mission in 2015. And photographed by the same mission 4 years earlier was this one, Vesta, another small planet. And you can see it's got big craters on where clearly other bits of asteroid have collided with it. But most asteroids are not baby planets. They're odd things like this peanut-shaped Eros. It's a lightish coloured one, and the lightish coloured ones are classified as S-type asteroids in general. And then there's darker ones like this fellow Matilda, which is a C-type asteroid. So they're not all the same, light ones and dark ones. And one of the things about them is they're spinning, but they're never spinning very fast. They have a slow spin. Also, when spacecraft have gone by them, it's been possible to work out the mass and hence the density. And they have low density, much lower than rock. And they have these odd shapes. And this has led to the view that most asteroids are basically piles of rubble. And that concept of rubble pile asteroids has been borne out by some recent expeditions. This is Ryugu, which was sampled by the Japanese Hayabusa 2 mission and brought back pieces which are now being well analysed. And a close-up of the surface, look, it's a pile of broken pieces of rock. And the same for Bennu, which was explored by the OSIRIS-REx mission, and samples were returned just a few weeks ago. It's just a pile of loose pieces of rock. So we get the impression then that the asteroid belt's a few planets and mostly broken pieces of rock in piles. And what seems to have happened is that asteroid planets have collided with each other and broken up, and the broken pieces have fallen back together again as loose aggregates under gravity to make the rubble piles. Now, we shouldn't forget that some meteorites come from the moon and from Mars. And these, of course, are launched when large pieces of asteroid collide with the moon or Mars and make a crater, and bits of the moon and Mars end up launched into space, and some of them come to us as meteorites. Okay. Now, the question is, what produced this asteroid belt? In fact, really, the question is more than that. What produced the planets in the orbits around the sun? And this cartoon shows the planets all going the same way around the sun in the same plane. And this idea, this observation, I should say, has led to the idea that the solar system began as a big disk of gas and dust going around the sun, like this artist's impression displays. There's the new sun in the middle, a huge disk of gas and dust in orbit around it, a bit like Saturn's rings, only much, much heavier. And then that dust is aggregating to make small planets, sometimes called planetesimals. Well, the story goes that these planetesimals created by spontaneous self-gravity from the dust, and then they merged with each other to make bigger planetesimals that merged again to make even bigger ones, until eventually we ended up with the planets. But somehow in the asteroid belt between Mars and Jupiter, things didn't work out to plan. And instead, we have no planet there. We just have a few baby planetesimals left behind and lots of broken planetesimals. So when we sample meteorites, we're looking at leftovers from this very early stage in the solar system when the planets were beginning to form from the dusty disk. And the idea of a disk going around the sun in this way has recently been corroborated by some remarkable photographs, like this one here. This is a disk around a young star about 450 light years away called HL Tauri. And it was imaged with a radio telescope, or really an array of radio telescopes in the Atacama Desert. The resolution with these is better than the resolution with the Hubble Space Telescope, but it's radio waves, not light. So there we are, disks around young stars, and that's how it all began. And our asteroids are failed attempts to make a planet, just leftover broken bits. Okay, so with that, let's turn to the meteorites again. And this cartoon shows a pie chart showing different kinds of meteorite. And as I said, iron meteorites make up about 6% of the total. This is the percentage of those that are seen to fall, as opposed to the fines. So 6% of those that fall are irons, and about 6% are basalt meteorites. And the great majority are these ones with the flecks of metal in, called chondritic meteorites. And then up here, 2% just of the obscure kinds, like I showed you, those made of olivine and those with big chunks of olivine embedded in metal. So we'll come to see those in a bit more detail now. And I'll start off with the iron meteorites. And there we are, enlarged. It's got a very interesting pattern of bands running across it, intersecting each other. And this pattern is called the Widmanstetten structure. And, and it comes about from theory and from experiment. It comes about by very slow cooling of iron metal, hot iron metal. And we believe this iron metal was once molten and it cooled down, solidified, and after it had solidified, as it cooled through about 900 degrees C, a change started to take place in the crystal structure of the metal and led to this pattern develop. And the pattern can only develop if the meteorite's cooling very, very slowly. When I say slowly, that's about 1 degree centigrade to 10 degrees centigrade in a million years. That's enormously slowly. So whatever that means, we'll come to in due course. But it is, I will say that the iron meteorites are not all the same. And in fact, there's about 15 different groups of iron meteorites. And this diagram shows iron meteorites that have been analyzed for cobalt and gold. And when you look at those two trace elements in the iron meteorite, they fall into clusters, and each cluster is a group. So each cluster is thought to come from a different asteroid. Okay, so that's our iron meteorites then, a number of different ones, and they cool down very, very slowly. Let's go to the basaltic meteorites. Basalt is an igneous rock. It was once molten, and it's made of dark and light mineral grains. I won't mention their names now, but just to show it's speckled looking. And we're all familiar with basalt because it comes out onto the surface of the Earth through volcanoes, and it's at about 1100 degrees, very hot, and cools down and freezes. And if you look at a basaltic meteorite through a microscope, this is what you might see. And this is a thin section of a basalt meteorite. Now, a thin section is a very, very thin slice. It's made by taking a slab of basalt, in this case, polishing one side and gluing it onto glass, and then grinding the excess away until you're left with just 0.03 millimeters or so of rock left. And then when you shine a light from below, you can see right through the rock and see its structure in enormous detail. And you can see, I don't know if this shows up, fairly whitish grains here and the brownish ones here. Those are the ones that are light and the dark flecks in the photograph. Okay, some basalt, some meteorites then are made of basalt, which was once molten and has cooled down and gone into these light and dark crystals. So on then to the most abundant kind of meteorite, called chondritic meteorites, or some people just call them chondrites. And there you can see the flecks of shiny metal embedded in rocky material, which is in this case gone a bit rusty, so it's brownish. This particular meteorite was found and had been sitting around on the surface for a while. It's just rusted a tiny bit. Well, when you break a chondritic meteorite, you might see inside the main ingredient. And this is an image taken with a scanning electron microscope. So you can see the three-dimensional surface of a broken chondritic meteorite, and it's got little spheres in it. And these are called chondrules. And these are made of silicate material, rocky material, and they were once molten, but they've cooled down and frozen. If we look at a chondritic meteorite on a polished surface with light shining onto it and reflected back, it might look a little bit like this. So the silicate has got darkish grey, but the metal is now bright and shiny. But we can also look at chondritic meteorites in a thin section, and this is what one might look like. You can see the round shapes of the chondrules. These are spheres that have been cut through. So you see a circular outline. Here's another one over here, and a few more irregular bits, like maybe these are broken chondrules. And then the black material is not letting any light through. That's the metal. And then there's it can't really point it out here, but there's fine-grained material in between everything called matrix. So chondrules and metal and matrix are the main ingredients of a typical chondritic meteorite. Now I'm going to say quite a bit about chondritic meteorites, but I'm going to start by saying the most important thing about them is their chemistry. If you analyze them chemically, they turn out to be the same as the sun. Okay, here's a graph showing chemical elements, and these numbers 2, 3, 4, 5, 6, 7, they're orders of magnitude. So 4 is 10 times more than 3, 5 is 100 times more than 3. So from very scarce elements right through to the most abundant ones like magnesium and silicon, so on at the top there, one for one, they're the same in the sun, which is the vertical axis, as they are in chondritic meteorites. So the first question I would ask is, well, wait a minute, I can analyze something in the laboratory to get the horizontal axis, what the meteorite contains. How on earth can you analyze the sun? It's a bit hot, you can't go and get a bit very easily. But fortunately, sunlight carries the information about the sun's composition. If you look at a spectrum of sunlight, red, orange, yellow, green, blue, and violet, like this, and stretch it all out, this has been stretched into a very, very long line and has been stacked so it fits on the screen. But what you can see there are dark lines at different points going through the colors. And each of these dark lines corresponds to one of the elements in the sun's atmosphere, the sun's photosphere. And the darker the line, the more of the element there is. They're called absorption lines. So from these dark lines in the sun spectrum, we can work out what the chemistry of the sun is. Indeed, the chemistry of distant stars can be analyzed, measured in the same way. Okay, so the sun is the same as chondritic meteorite. So does that make sense? Well, of course it does, because when we go back to this idea of a disk of dust and gas going around the infant sun, it's all made of the same material. The sun in the middle and the disk are all made of material with this chemical composition. It's sometimes called a primitive chemical composition, or solar composition, or chondritic composition. They're all the same. Chondritic, solar, and primitive are 3 words to describe this composition. I should have mentioned when I was here that we don't include in those elements the hydrogen and the helium that make up most of the sun. These are only the elements that condense easily, not the ones that stay in gases. Okay, so primitive chemistry made the sun and made the disks, and the chondritic meteorites preserve that chemistry. So they're like starting material for the solar system and for the planets. Okay, so let's go back to chondrites again, and here's another aspect of them. On the left, there's a chondrite. We can see the chondrules circular in the thin section. And here you can hardly make out the chondrules, and here you can't make them out at all. And this is because going from one of these, they're 3 separate meteorites. The one on the right has been very strongly heated. It's become a metamorphic rock and taken on a new arrangement of its components. The black is the metal and the colorless stuff is the silicate, but it's been strongly heated. And if we go a little bit further and imagine it becoming heated even more, then the chondritic meteorite would start to melt. And we imagine something like this happened. Chondritic meteorite gets heated to the point not that it just gets baked and changes its appearance, but it begins to melt. And liquid basalt magma is produced, and that comes to the surface of a small planet to make basalt, and the iron flecks melt, and they are dense, and so they sink down to the center of the planet and make an iron molten core. And as it cools down, that molten iron core will solidify and harden. So in a cartoon like this, we can think of this small planet, chondritic planet to start with. It gets heated up, and metal, shown in red here, goes down to form a core, and basalt would make its way to the surface and end up forming a basalt outer coating. But the story is not quite as simple as chondritic meteorite just splitting to make iron and basalt. What happens when it gets heated up? It doesn't go into total melt. It goes into a slurry, crystals and liquid. And the basalt is only part of it. The little bit of liquid that forms is basalt, but there's an awful lot of olivine left behind. So what we tend to get is iron going to the middle, basalt coming to the surface, and a lot of this olivine rock left behind. So our cartoon for melting would probably look more like this. Well, sorry, there's a meteorite made of this olivine rock. This is an interior of a planetesimal that's been heated to melting. The basalt's moved upwards, the liquid iron has moved downwards, and this is residual or leftover olivine in the middle. And the cartoon would look like this: chondritic meteorite material to start with, you heat it and melt it, and you get basalt to the surface, leftover olivine in the middle, and iron meteorites forming the core. And of course, in a core, the iron would cool down really rather slowly, which is consistent with this very, very slow cooling rate that gives rise to the Widmanstätten structure. So everything is beginning to fall into place. And also falling into place are these meteorites I showed you at the beginning, iron metal with olivine crystals embedded in it. These meteorites are called pallasites. And they would correspond to, if I go back to the boundary between the residual olivine and the metal below. And if they don't separate out properly, or if maybe they get shaken together by a collision afterwards, metal and olivine mix together, from near that boundary between the core and the olivine surrounding it, we end up with pallasites like this. And this is a lovely picture of two lucky fellas who went out with a metal detector on their farm and found this chunk of pallasite. So they're probably living off it ever since. Okay. So much then for the origin of the different kinds of meteorite by heating and melting of chondritic stuff. So let's go back to the chondrites again and look at some other aspects of them. And one of them is that they're not all the same. Here's one. This is the Bovidi meteorite that landed in County Derry in 1969. You can see it's got chondrules in. Well, they're not so easy to see, but you can certainly see it's made of lots of bits. And here is a very different chondrite. It's grayish in color, and also you can see bits in it, but they're not the same as each other. And chondrites differ from one to another. They've all more or less got the same chemistry as the sun, but they differ a little bit in the detail of their ingredients. And they have been divided into, they fall into about 15 separate categories. One of the ways of distinguishing between them is to look at the oxygen in them. Oxygen is an element you all know about, but oxygen is made of 3 different kinds of oxygen atom. 16 is the main one, oxygen 16, and 17 and 18 are 2 other kinds of oxygen, and they're always mixed together in more or less the same proportions. And in meteorites, they are a sort of fingerprint for the kind of meteorite, and these letters R, L, LL, H, and so on, these are each different groups of chondritic meteorite that differ from each other according to their oxygen isotopes. Okay, so we think that they come from maybe 15 different small planetesimals that broke up. And another thing about chondritic meteorites that you might be interested in is that, of course, the asteroids were colliding and breaking up. And when they collide, if they do it at any speed at all, there's a lot of damage done. And we get things like this. Here is, this is the one that landed in Russia, Chelyabinsk, that I showed you the fireball of at the beginning. It's broken up bits of chondrite, all kind of knocked together again. And this breaking up happened before it hit the Earth. This happened in space early on. And it's called a brecciated chondrite. And so that's one of the signs that this poor rock has been bashed by collisions in space. And another thing that happens when collisions happen is that individual mineral grains, this is a thin section, but it's taken with a Polaroid filter in, but the grains have been shattered and broken as a result of the shock when two different planetesimals collided. And sometimes the shock is so great that you get minerals changing. So this is mostly olivine in this area of this particular chondrite, but these blue crystals are not olivine. They're something with exactly the same chemistry as olivine, but it's much denser than olivine. It's called ringwoodite, and the ringwoodites formed because there was a massive increase of pressure, shock pressure, when there was a collision, and the olivine transformed into an equivalent called ringwoodite. So we get evidence, as you might expect, in the meteorites of the collisions that have taken place between planetesimals. Okay, now here's something else that's found in chondrites, particularly the darker carbonaceous chondrites. They're called calcium aluminium rich inclusions. They're called that because the grains in them are minerals with a lot of calcium and aluminium in. Calcium and aluminium are the elements that are left behind when you've really heat a meteorite up to nearly everything vaporizes. They're the last things to leave. So they're concentrated in these CAIs. And these CAIs are of interest because they turn out to be 4,567 million years old. Pretty well all of them are the same age, 4, 5, 6, 7 million years old. And that's the oldest age obtained from a meteorite, and it's taken as the age of the solar system. So it's a nice, easy number to remember, 4, 5, 6, 7 million years. Okay, now the element uranium is also an element that doesn't boil. It stays behind when everything else evaporates. So there's a trace of uranium in these CAIs. And uranium changes very slowly into another element, lead. And that's the basis for this age. Let me see if I can explain to you how we know that age, 4, 5, 6, 7 million years. Okay, so newly made CAIs contained a trace of uranium because it didn't evaporate, but they didn't contain any lead because the lead is volatile, it boiled off. But today they contain some lead. Now, why is that? Well, it's because the uranium, it changes very, very, very slowly into lead. It's said to be radioactive. But the change is extremely slow. So if you start with 100,000 million uranium atoms, wait a year, only 15 of those atoms will have turned to lead in 1 year. It's hardly anything. And we can measure, using an instrument called a mass spectrometer, we can measure the amount of lead that's in one of these CAIs now, and we can measure the amount of uranium that's still left. Now, knowing the rate of change, that's 15 atoms per year out of 100,000 million atoms, knowing the rate of change, it's possible to calculate how far back in time we need to go to the time when there was no lead, just uranium. And that's the age of the CAI, 4, 5, 6, 7 million years. Here's a picture of a mass spectrometer, very expensive piece of kit. And the CAIs tell us something else that's interesting. Oh, I should just put this in perspective. There's our solar system 4, 5, 6, 7 million years ago, and it's pretty close to a third of the time since the Big Bang, nearly 14,000 million years ago. Okay, so I was just about to say that CAIs tell us something else that's interesting. And that is they provide evidence for the heat source that caused these chondritic planetesimals to start melting. They contain proof that radioactive aluminium, that's an isotope of aluminium called aluminium-26, was present alongside the normal abundant aluminium, which is aluminium-27. And the reason we can know this is that when aluminium-26 is there, it doesn't last very long. Half of it's gone in about 0.71 million years, 700,000 years or so. Half of it will have gone. So after a few million years, it'll be pretty well all have gone, this aluminium-26. But when it changes, it goes to magnesium-26. So if you've got an excess of aluminium-26 around, and since calcium aluminium rich inclusions have got a lot of aluminium and relatively little magnesium, then this excess of aluminium-26 at the beginning shows up in the magnesium that it changes into, and we have an excess of magnesium-26 in these CAIs. And that excess, the amount of that excess, it allows us to work out that there was so much aluminium-26 around at the beginning. And that was more than enough aluminium-26 to cause heating, because when aluminium-26 changes into magnesium-26, it yields a lot of heat, more than enough to do the melting that we want. Okay, so with that, I'll leave meteorites and go back to the big picture and look at solar systems, stars with disks around them, like this lovely picture of H.L. Tauri, and what our solar system was probably like when it formed. So where do these young stars with disks around them come from? And the answer is that they come from huge clouds of gas and dust in the galaxy. This H.L. Tauri is in one of those clouds, a relatively small one, 450 light years away, but a little bit further out, 1,500 light years away, is Orion. It's a huge cloud of gas and dust, the Orion Nebula, as it's called. And in this cloud of gas and dust, new stars are being born. And this cartoon shows effectively what happens. There's the huge cloud of gas and dust, huge cloud, and fragments of it start to collapse in on themselves and get smaller, and the angular momentum of the collapsing cloud fragment is maintained. So it spins faster and faster, and a disk forms around the central star like that. And if you want to see what Orion might have been like, this fellow, Matthew Bate, has done some lovely models, and a video shows what might have been going on in one of these collapsing clouds. So if I play this now, hopefully, there we are. It lasts about a minute and a half. It's collapsing. It's going into filaments, and the filaments shrink along a length into lumps, which are going to become new stars. And each of these stars will be spinning and will therefore have the potential of a disk of dust and gas going around it, which will become a planetary disk. There we are. And you can see that the newly formed stars are being flung out as they feed into the central spiraling part of the cloud as it's collapsing. Quite amazing modeling of what goes on in one of these huge clouds of gas and dust like we see in the Orion Nebula. So this was happening 4,567 billion years ago. And incidentally, the dust that made our solar system, something happened to it to make it radioactive with aluminium-26. That aluminium-26 doesn't last long, so it must have been made during this period of star formation somehow, but we're not quite sure how. Okay, so that's how stars were formed. But next, the question is, where does the dust in one of those big clouds of gas and dust come from? And one of the sources of dust is from stars that reach the end of their life and explode and become a supernova explosion. So in 1054 AD, this was a star, and it suddenly got very, very bright, and it's been expanding ever since, shedding its contents back into the galaxy for recycling. And again, going back to chondrites, I've mentioned various things that are found in them, chondrules and metal and matrix and CAIs, but we find in some of the ones, particularly the ones that haven't been baked at all, things like this, little grains. And this is a grain of silicon carbide, and we think this is a grain that's nothing to do with the solar system. We think this is a grain that's a hangover from a supernova explosion that happened before the solar system was formed. And the reason we think that is that the carbon atoms in it are two kinds, carbon-12 and carbon-13. And normally, in everything around in Earth or any meteorites as a whole, 89 is the ratio of carbon-12 to carbon-13. And the giveaway is that the carbon-12 to carbon-13 has got a ratio in this particular grain of, sorry, let me go back to that, has got a ratio of very, very different number, 39. And different silicon carbide grains have been extracted from meteorites, and they've got not all 39, they're all, they vary a bit, but they're not the same as the solar system. So we regard these as tiny surviving bits from supernova explosions that happened before the solar system was made, that fed into that cloud of gas and dust from which the solar system was made. Okay, so let's have a summary, and I'll just read this. 4,567 million years ago, with the universe 2/3 through its history, the sun was born by gravitational collapse within a huge cloud of gas and dust in the Milky Way galaxy. The dust in the cloud came from old stars that had exploded, recycling their contents back into the galaxy. And the infant sun was surrounded by a flat, rotating disk of galactic gas and dust. And chondritic planetesimals grew from the dust, and many of them got hot and melted to make the iron meteorites and the basalt meteorites, and they collided and merged repeatedly to make the planets. But no planet formed in the asteroid belt. Instead, the asteroids include rare planetesimals that escaped being added to planets, and rubble piles of collision fragments from broken up planetesimals, and pieces of asteroid make their way to Earth as meteorites for us to ponder. And I will leave it there. My time is up, and I'll thank you all for listening.
Thank you very much indeed, Ian. Now, if you had any questions, we suggest you pop them into the chat. But if you want to unmute your microphone and just shout out your question, feel free to do so now. Well, while they're all getting over their shyness, I can tell you a fascinating talk. I've heard you talk about meteorites before, and it's amazing. In the last few years, we've come quite a way. That simulation is superb. And so maybe I'll ask a local question just to kick things off. The Lachlan Bridge meteorite. Do we know much about that? Did you talk too much about?
Well, I'm a little bit skeptical about its authenticity. I hate to say it, because it's nice to be able to claim that Ireland had the last meteorite fall of the millennium. It landed in November 1999. But there was a brilliant fireball, and you predicted where it would fall. But the person who found it remained a little bit mysterious. He was a dealer, meteorite dealer. And he claims that he got it from a little old lady who found it lying on the road and didn't want anyone to know because she was afraid that the taxman might be after her after she'd sold it. Now, who do you trust Now, what worries me is that another bit was found. It's not just the one piece, and that stretches credulity a little bit for me. And I'm just wondering whether that was already it's an ordinary common kind of chondritic meteorite. There's nothing special about it, and it's quite possible that it existed. But I won't go further down this track because we don't know. It's just a bit unfortunate that the finding of that Lachlan Bridge meteorite was a bit shrouded in obscurity, and it would have been much nicer if it had been like the farmer who found the Bavidi meteorite and showed us and handed it over to the museum and all the rest of it. So there we are. Is that dented your confidence and trust?
I'm just, I'll ask a really quick question. I'm just wondering, what is olivine made from?
Oh, yes, you're right to ask that. It's made of three chemical elements, which are very, very common elements in the solar system as a whole. Oxygen, which is the most abundant element in the solar system, followed by magnesium and silicon. And those three elements combined make up olivine.
Okay, thank you.
So, thank you for asking. I'm sorry I forgot to mention that.
Yeah, we'll just come to the highlights, what to see in the sky in a moment, and the other events for Science Week. But I don't know if you're good with chat, Ian. There's a question in the chat box. Maybe I'll read it to you.
It's
sorry,
I should look at the chat.
Tortoma, and the question is, why do the forming of new stars rotate? Probably means why do the formation of new stars rotate? Why are they always spinning?
As far as I know, it's to do with conservation of angular momentum, and as they get smaller, the angular momentum has to be maintained, so they have to spin faster, and spinning faster prevents everything falling into the central mass, and some of it is stuck out there in the rotating disk. That doesn't really make sense? I don't know if you've seen ice ballerinas who pull themselves in tight and spin very much faster. So in a way, a collapsing bit of the cloud that makes a star would be spinning faster and faster as it shrinks.
I think that explains it well. Yeah. Do we have any other questions, or will I? Oh, we have. Oh no, we have a reply. I understand. Thanks. Great. Well, look here. If you want to stay with us, if anybody has any questions, they can contact you through your TCD email address, I'm sure.
Yes.
Because whenever anybody finds a guilty-looking rock, we always send them your way to isanders@tcd.ie. There's a couple of things popped up in the chat, but they're just thank yous. That's okay. Thank you very much. So look, given the time.
Hi, David. Can I just ask a question, please?
Yes, please.
What is the normal weight of a meteorite?
Oh,
because I saw something. I think it must have been up in the planetarium up in Armagh, and it was extremely heavy. And I saw you holding a piece of rock there, like as if it was nothing. So, is there a difference in the weight?
Well, I think you're really asking me about density, because the weight depends on how big it is. If it's big, it's heavy, and if it's small, it's light. But the density is something that's important. And an iron meteorite like this, that is, well, it's just like holding a piece of iron. You know, it's about 7 times heavier than water. But stony meteorites, like the basaltic ones, they are not so heavy, not so dense as the iron ones. But so they're mostly heavier than ordinary terrestrial rocks, and iron ones are particularly heavier for their size. Okay,
thank you.
And we had another question there, just came up in the chat section. Good question from Carl Fleming. Are there any meteorite samples viewable in any Irish museum?
Well, if I hate to say it, I haven't seen that. I'm just trying to whether there was a piece. There was a meteorite. I'm showing the beggars, not beg the beggars bush bar, not beggars bush bar, the museum
Collins Barracks, isn't it?
Collins Barracks. Yes, there was one there. I'm not sure. Is that I've heard that show is being recycled or closed. Certainly, if you go up to Belfast, you'll see meteorites in the Ulster Museum. No, I better do some homework and just check up where they are visible.
Yeah, if you want to see any of the meteorites, if you do contact the National Museum, they do sometimes put them on display. Many years ago, 10 or 20 years ago, I opened an exhibition for them where they had bought pieces of Mars and pieces of the moon. So there are meteorites from Mars and the moon in the Irish state's possession, shall we say. So hopefully they have them on display. It's a good point, actually. We should check out if they are on display.
No, they should be on display permanently.
Yeah, if anybody finds out, do send a note to our social media so everyone could go in and see them. If not, let's ask them to put them back on display.
Absolutely.
So many things to display.
Absolutely, yeah.
Okay,
David, Ian, sorry.
Oh, we have no question? Go ahead.
Yeah, quickie question for Ian and yourself. How did they know that that there was a specific meteorite, I think, and they maintained that it was from Mars? And I think it landed in the Arctic or Antarctic. There was a discussion whether they had some kind of life embedded in it. They were doing it under a microscope, looked like a worm or something like that. Probably a couple of years ago now.
Well,
how do they know it's specifically from a planet as opposed to a space wanderer, you know?
So you're really asking two questions. One, how do we know it was from Mars? And the second one is was it life? We've known for a while that some meteorites come from Mars, partly because basalt is produced in Mars much more recently. So these are much younger meteorites when you date them than others. But more importantly, the first Martian rover was able to measure the composition of the atmosphere in Mars. And a meteorite had a glassy meteorite that had been melted and then frozen, had little gas bubbles in it. And those little gas bubbles in that meteorite turned out to be an identical match for what was then known to be the composition of the Martian atmosphere. So that really clinched it. As to the worm-like thing you mentioned that was thought to be life, it turned out to be not so. It's been documented that can form by totally abiotic processes. Okay.
That's great. Thank you very much.
Sorry to disappoint you.
No problem. Thanks.
And I think, unfortunately, no life on Mars just yet. But there are Martian meteorites around, very collectible, very expensive.
Yeah.
I heard there was 30 or so. Has a good number gone up?
I forget what the last count was. It's sort of that order, yes.
Yeah. And there's something like years ago, there was something like 30,000 meteorites known.
No, I updated that. 65,000 was tonight's number. And it's probably more like 70,000. They're appearing on the market at such a regular rate, mostly from North Africa, but every year they have Antarctic expeditions to collect from the blue ice field. So the numbers are enormous, up 70 or 80,000, I guess. And new things are coming to light all the time that we haven't seen before, and filling in all sorts of details in just what was going on in that early solar system.
Right. Yeah. Well, one aspect of Science Week is to inspire the future. So if any young future meteorite researchers out there, there's loads more meteorites to work on.
Yeah,
an active field of study.
Yeah.
Okay. Well, thank you very much. We'll leave it there for Science Week. Brilliant talk as ever. Thank you very much for doing it. I'm sure we'll have you back when we do find life in a meteorite. Something. You can hang on with us if you want. I'm just going to tell people briefly what to see in the sky and also the events coming up for Science Week, and then we'll close the meeting in about 2 or 3 minutes' time. Thanks again, Ian. So, if you get the magazine, and if you don't, you have to sign up for it. What I always tell people is go to page 22 the moment it drops through your letterbox and read the highlights box, especially anything with 3 stars after it, because that'll tell you what's coming up, maybe an eclipse or something. And one thing I forgot to mention at the start, of course, we had Venus passing behind the moon on November 9th last week. And my trick for beating the Irish weather works great when the event happens for several hours, like the eclipse on October 28th, but it didn't work for me on November the 9th because Venus only took 2 minutes to pass behind the moon. I got to see it going up very close to the moon. Then the clouds rolled in for those 2 minutes. And then Venus appeared from the other side about an hour later, and it was cloudy again. And then a few minutes after that, the skies cleared again. So it's as if somebody up there knows that what we're trying to watch and is out to thwart us. But the important thing is that other people got great pictures. Before the sun rose, you could see Venus extremely close to the moon, and the magazine would be packed full of those Irish photos as well. So what else is happening? It says here, on November 17th, the International Space Station starts to cross evening skies. Predictions for that every day till December 6th on our social media. Then on the 17th, there's a Leonid meteor shower. Now, it produces about 15 meteors an hour, maybe less, certainly less if you're in not a perfectly dark sky. So, if you like sitting out waiting 10 minutes for a meteor, great, but I tend to wait for the big ones, which are the Geminids in December, and the Perseids in August. And the Geminids now is by far the best. And that is going to be moon-free, just like the November Leonids are on November 17th. So maybe practice on the Leonids, but definitely be ready for December 13th and 14th for the best meteor shower of the year by far. The magazine also details when Saturn is near the moon, November the 20th, Jupiter's near the moon 4 days later. The Pleiades star cluster is a lovely sight right next to the moon, though the moon will be full at the end of the month when that happens. And there's loads more to see in the magazine. One other thing we'll be telling you about is Comet Lemon. It just passed closest to the Earth. I've seen one magnitude estimate putting it magnitude 5.9, which means faintly visible to the naked eye. If you have a really dark sky, I've been getting some pictures of it. They'll be going to the magazine. Blob. Other people have got pictures of it too, with better equipment than me, showing lovely tails. So that's the brightest comet for a while. Good one to practice on as well, because there are some much brighter comets, perhaps 10 times brighter or more, coming next year that we can predict. And remember, Comet Lemon was only discovered in April of this year, so we don't know what's going to happen next year with comets. And the comet we had, Nishimura, recently, that we saw at the end of the Starbecue in September, that was only found about a month before it became second magnitude. That's brighter than the Andromeda Galaxy or the Orion Nebula. Unfortunately, it was in twilight at the time. So refer to your magazine for more events in the sky. Events on the ground for Science Week. Our classes happen every Tuesday. You can join them now, even though a few of them have taken place. They're all self-contained. You can watch the ones that are coming up. You can actually get recordings of the ones that have already happened. And then you can repeat the entire course at the end of January when the course is repeated again, free of charge. So no need to wait till January. Go to astronomy.ie/class and sign up now if you're a beginner and you want those 8 classes. There's more details of what's covered. I'm in Tralee, County Kerry on Friday in the Shimshatira Theatre, 350 people listening to a talk on the universe. We have one tomorrow in Leitrim, but that's sold out. And there's another one running then in Mayo, in Cong in Mayo. All these details are on astronomy.ie, our website. And that'll keep us very busy for the rest of the month. And the big event for telescope use is our Saturn watch next week on the 21st of November. So that's tomorrow week. It's actually one of our evening classes as well. So evening class people will be coming along or tuning in online to find out all about telescopes, regardless of weather. And hopefully Saturn will appear and we'll get to see it through the giant telescopes. And it's going to be one of the most incredible sights you'll ever see in a telescope. This bright star in the sky is transformed into this big globe with those beautiful rings and several of its moons. And no photograph does it justice. There's something ethereal about the light seen through a telescope live. that you just can't reproduce, even in our magazine or on a laptop or a phone screen. So do come and have a live view at least once in your life. Bring the whole family. We do everything, point the telescope. You just have to look in. You get tickets for that as well on astronomy.ie. So that's everything that's coming up. Just needs me to tell you about our next lecture. As I said, we have them every month, usually on the second Monday of the month, and December is no exception. So on December the is it the 9th? Better check my notes here. December the 9th, we have a very interesting talk by Dr. Steve Barrett from the University of Liverpool. Steve has given us several talks before. This one is perfect on December the 11th for the season that's in it. It's the science of Santa Claus. If you want more details of that, go to astronomy.ie, go into the events section. You'll see that there. You can get your tickets now. I said, if you want DVDs of past talks or on the online links to them, check out the website as well. It's going to be very busy for Science Week. If you go to our Science Week page, you'll see there's other groups running all kinds of science activities all over the country. Do check them out. So unless I've forgotten anything, Laura, I think that is everything we have to say this evening.
I think so. I don't think
Other
you've missed anything.
volunteers have anything to add? I'm a devil for leaving things out. Oh, great. Well, look, we might see some of you in Tralee. I know some people from Kerry have booked tonight's talk, or in Mayo, or even in Leitrim tomorrow. So if you want us to come and give a talk in your area, especially to schools or other groups, just contact us. We'd love to do so. So thanks everybody for watching, and a huge thank you to Dr. Ian Sanders from Trinity College for a brilliant talk on meteorites. I learned quite a bit myself again. So I'm looking forward to learning more the next time he gives us a talk. Thank you, everybody, and good night.
Good night, David.
Good night.
Very well.
Okay, Laura, I've stopped the recording. Do you want to stop the YouTube one?